Swayam Prabha. Digital India. Educated India.
So after learning about the shear force diagrams and the bending moment diagrams and how the shear forces and the bending moments vary along the length of the beam depending upon the loading and the beam support conditions, now we are going to focus on the theory of simple bending. And in another words, it is also known as the pure bending. Now, you might be slightly misled by what do we mean by pure bending or what do we mean by simple bending. Well, I mean it of course means that you're removing the effect of shear in while you're calculating the section displacements and the section deformation. So you're purely focusing on the effects of bending and the pure bending. And the theory of simple bending essentially says, another name for pure bending essentially says, that we are looking at places or sections within the beam where the bending moment stays constant. Now, in real life scenarios, as you saw while you drew the shear force diagrams and the bending moment diagrams, there are, the bending moment it varies along the length of the beam depending upon the loads and the support. So the formulations and everything which we are going to derive by looking at sections of the beam where the shear is 0 and correspondingly the bending moment is a constant, this can also be applied to the non-uniform bending unless you have a sudden jump in the moment. So if you have places where you have a kind of a transition of the moment, if you take smaller chunks of the regions of the transition, there roughly the bending moment is more or less constant. So some of these concepts which we are going to discuss will still hold over there. Now, one classic example of the pure bending or the simple bending, as you see over here, is the weightlifter, and we will see in a couple of pages that why this is a case where there are regions within the beam, in this case the rod, the shear force will be 0 and you will have a constant bending moment, right? So let's go ahead and start with this particular topic. So first of all, let's see some of the examples where we take a look at the pure bending, that is, there is no effect of shear. So one of the examples is this one, where you have a simply supported load with two moments m1 and m1. If you draw the shear force diagram for this, is you will have a 0 shear force and consequently you will have a constant bending moment. Now, why we have a constant bending moment? Now remember that the formula which we had derived while we were looking at the relationship, that my dm dx was equals to v, right? So for moment to be constant, for it to be a case of the simple bending, which means a moment is a constant, or a pure bending where a shear is 0. So if you put a v equals to 0 over here, that means your moment is a constant bending moment, right? So this is one of the cases. And here you can say that since this beam, if you just take a look at the moment, how do we expect this beam to bend? This beam would most likely bend something like this over here, right? So it is a positive convention. Remember the sagging effect, which we term as positive over here. And as you see the bending moment, the entire bending moment is in the upper half plane. It's a positive m. In contrast to that, if you look at the second beam where you have a cantilever and you're applying this moment m2 over here. So if you have a cantilever and you're applying, this is a kind of a moment m2. So what you're seeing is a sagging kind, is a hogging kind of a moment. Sorry. So this beam, bends something like this. Right? So it is a negative bending. So that you can see here as well. So the entire bending moment diagram is in the lower half plane with a value of minus m2 over here. In both these cases, the first two cases, the shear force is 0 along the entire length of the beam. But if you take a look at the third case over here, here you have a beam where two intermediate loads P. So as a result of which you have two reactions P and P over here. Now if you draw the shear force diagram for this beam, if you follow closely the relationship, so here you start with a vertical P over here, you go for as a constant line, and here you are meeting a concentrated load. So there is going to be a jump in the shear. So what was P, it comes down back to 0. And then since there is no load in between, you get a constant of 0 shear force, and in this region you can say that you will have a constant bending moment of PA over here. Right? So now this case is also very similar to what we looked at the weightlifter. So if you see the weightlifter's hands over here, at the two ends you have the two loads which are going down, and intermediate you have the support. So it's essentially it is the similar beam like this, just flipped. So for the weightlifter's case, you will have I should have drawn this slightly below. Let me just draw it below. So the weightlifter's case, it will be something like this. So where you have the weights which are going down, the two end loads which are there, and intermediate you have the weightlifter's hand. So if you draw the shear force diagram for this one, it will be something similar to this one, but it will be just flipped. So this rectangle will be down and this rectangle will be up over here. And in this case also, this particular region that you're looking at, this particular region will also be a constant bending moment. So you will have a pure bending case there as well, right? So now that we know that what a pure bending is, so essentially it is sections where the bending moment is a constant. So in those regions where the bending moment is a constant, how does the beam deflect, or how does the beam behave? Let us take a look at it. So if you consider sections in pure bending, right? So sections in pure bending, it bends the beam into the arcs of a circle. So if you have a beam, regardless of the cross section, remember we are always in the back of our mind, we have this, that the cross section of the beam has to always be a rectangular cross section. That is not the case. Your beam can have, different, as long as it's prismatic, all these derivations that we are going to do, all these assumptions are valid. So instead of being a rectangular cross section, if it's a circular beam or a beam which a trapezoidal shape like this one over here, if you have the pure bending where you have the constant bending moments, it is still going to bend in the arc of a circle that you see over here. So what it essentially means is that you will have a radius of curvature. So let's say the radius of curvature is rho over here, right? And this rho along that particular arc stays constant. So if this is my point D intermediate over here, and I mark two more points, say B and C over here, at B the radius of curvature is rho, at D the radius of curvature is rho, at C the radius of curvature. So essentially it bends into the arc of a circle that is there. So now that we understand that how the phenomena of pure bending acts, how does it deflect the beam, and points along the beam where it bends, right? It bends into the arc of a circle, and in those regions we'll have the constant radius of curvature over here. Now remember, if you have to draw parallels between what is a positive curvature and what is a negative curvature, it follows closely with your concept of the bending moment. Now remember, for the bending moment, what we had studied is that if our beam bends like this, right, which is the smiley face, remember, if your beam bends like this over here, this is a sagging bending moment. So this is a positive M and a positive rho as well, right? On the other hand, if your beam is bending like this, right, then that is a negative M and a negative rho. So that is your hogging kind of a moment that you have. So this is sagging and this is hogging that you have over here. So let's go ahead and take these concepts a little bit further. So if you consider a beam, for example, this cantilever that you see over here, where at the end you are pulling vertically up with a force P. So the deflected shape of the beam is something like this, and from this you can tell that it is a sagging kind of a movement. So if you are doing like this, it is a sagging kind of a movement. So it's a positive curvature that you're looking at. So this is what we were showing. So it is a positive curvature and moment also. So let's make a note of that as well. And this is a negative curvature and a negative moment that you have, right? So here, if we now have to sort of write the formulations for the between the curvature and the angle over here, right? So since we are saying that this bends in the arc of a circle, so we have this rho over here, and say this beam was originally around the x-axis, and for small deflections, let's just try to write some of the relationships that might exist. So this length ds, which is that arc, a small arc of the circle, we can express that as my rho times d theta will be equals to ds, right? Where I know my rho, which I marked, rho is nothing but my radius of curvature. Now, what is the relationship between the radius of curvature and curvature? We have kappa. Remember, this is another Greek symbol which you're probably familiar with to represent a curvature. So we have this kappa, which is equals to 1 over rho, and kappa is nothing but the curvature. So the curvature is reciprocal of the radius of curvature that we have over here. So if we have to express, so what we can get from this these two relationships is that your kappa is equals to 1 over rho, which will be equal to your d theta by ds, right? So now for small deflections, if this amount deflection is small, and when we are talking about beams and so on, we're talking about small deflections only, this ds can be approximated to the original length dx. So typically this is written as, so for small deflections, we can write that kappa is equals to 1 over rho equals to d theta by d. So this is an important relationship. You will see that we will make a use of this one to derive some of the formulations and everything later. So this is the curvature or the radius of curvature, how it varies, and if it inscribes an angle of theta, how it is related to the curvature, that kappa equals to d theta over dx. Now moving ahead, let's now leave all this math and everything behind and just try to understand that how a beam deflects, and intuitively what are some of the the rules, what are some of the assumptions we can underlay when we are talking about the pure bending or bending in general. Right now, what I want you to focus is these figures over here. So let's just start with this one. So here you have a part of a beam. Remember the section lines that we had discussed, which is the part of a bigger beam. You are taking a small chunk of that. So, and as I said, it need not be rectangular, it can be any prismatic section that you have. So for this beam, say after a long distance, you'd have the point O over here, where you have this distance. This is your radius of curvature that you have over here, rho, which inscribes this d theta angle over here. So this is meets at a farther distance away, and that's why you have the section break line over here as well, right? And let's see that how and what kind of effects happen. So that is more important to intuitively understand. So first of all, if you take this beam over here when it bends, so let's just see. So you see these lines, these sections over here. For example, if you take a look at these sections, these vertical sections that are over here, these vertical lines that we have drawn, the black lines over here, when the beam is straight, they are straight, and when the beam bends, do these sections warp? No, they don't warp. They continue to remain plane. So if you take any one of these black lines, right? If this was the original plane section that was there, after bending, that remains plane. So there is no warping. If you take any of these black lines that you see over here, what was plane, after bending it remains plane. So what does that mean? That means your plane sections remain plane before and after the bending. So if you essentially take a cross section, so that was something like this, and it has only shifted. So plane sections remain plane before and after bending. Okay, what is another thing which we can see? Again, if you see over here, if you consider this top black line between the end vertical lines, this one and this one over here, if you see this top black line and the bottom black line over here, initially in the undeformed configuration, both these lines, the top one and the bottom one, are of the same length. Now when I am bending this one over here, can you see the change that is happening? The top line actually contracts and the bottom line expands. So what does that mean, and what kind of a moment is this? Is the sagging kind of a positive moment, right? So when I am doing this, there is a reduction in the length of the top line but an expansion in the length of the bottom line over here. So the top line contracts and the bottom line expands. Of course, if you're bending it the other way, you will have a different phenomena, completely opposite phenomena, where your top line is going an increase in length and the bottom line over here, this one is undergoing a decrease in length over here. So now if one of the lines is having a decrease in length, the top one, and the bottom one is having an increase in length, in between the top and the bottom, there must be one line which does not change any length at all, because the top one is decreasing, bottom one is increasing. So in between you must have a line where nothing changes. Okay, so what are the three things we looked at? First is that plane sections. Let me just go back to the page over here. So plane sections before and after bending remain plane. So there is no warping, there is no sections being twisted out of their place. So the plane sections remain plane. The top line over here, if you are looking at the positive bending moment case, the top line contracts and the bottom one expands. So the top point contracts means what? The top part is undergoing a compression. So you see it is undergoing a shortening in length. So that means the top line is undergoing compression, whereas the bottom part over here, the bottom top part of the beam is undergoing tension because it is going an expansion in length, right? And consequently, in between the top and the bottom, you must have a line which is known as the neutral axis. We will see in that particular line does not undergo any change in length. So that brings you to three of the primary assumptions of a pure bending, which are these ones over here. That is, it states that plane sections remain plane before and after bending. That's the first one that we saw, right? The second one is that the bottom of the beam is in tension, that it elongates, because initially both lengths were the same. Now the bottom one has elongated, the top one has contracted. So the bottom part of the beam is in tension and the top part of the beam is in compression. But remember, this is for a positive curvature only. This is for the positive moment and curvature. If you are, of course, making a hogging moment or a negative curvature or a negative moment, then this statement will just flip, that the top part of the beam will be in tension and the bottom part will be in compression, right? And the last one, the last assumption that you have over here, that in between the top and the bottom there must be a line. So if any of these horizontal lines over here which you see across the length of the beam, there must be one such line along which there is no change of length, because the top is shortening, bottom is expanding. So in between you must have a line which does not undergo any change of length, or in other words, it has no tension, neither compression, right? So these are the three fundamental assumptions that you see, or mostly facts, because for the pure bending these are facts. So plane sections remain plane before and after bending, bottom part of the beam is in tension, top part of the beam is in compression if you're looking at the positive curvature, and then in between you must have a plane which is very, very importantly known as the neutral axis, or you will see often in book this is known as NA, where there is no change in length, or essentially no tension or no compression. What we're going to do next is that we are going to take these assumptions and go ahead and we are going to look at the cases where we are going to derive the flexure formula, where we make use of some of these assumptions and also the curvature formula that we looked at. Now we are going to derive what is known as the flexure formula. So previously, if you remember, we have derived the the formula for the axial loading, the torsion formula. So now we are going to specifically look at the case of bending that is there. Now, if you remember, where we had left off was this beam which we were looking at under pure bending. So you have an M and an M over here, and some of the assumptions that the plane sections remain plane before and after bending and so on, and also the top part contracts and the bottom part expands, that is the top part is in compression, the bottom part is in tension for the case where you have the sagging moment, and in between you have a line which does not undergo any tension or compression or change of length, and that is known as the neutral axis. So in this beam, maybe let us mark this particular line that you see, this dotted line. Let's say that is the neutral axis for our beam, and there are ways to find this neutral axis that we will take a look at later. So we have this neutral axis where there is no tension and no compression, the length remains the same. Now before this beam, before you have applied this moment M, this beam is straight, right? So whether you're looking at a length of dx at the neutral axis, or whether you're looking at top or at bottom, the length of each of these smaller chunks is equals to dx that we have over here, right? But the moment you are applying these bending moments that are there, after that the length of the line along the neutral axis stays as dx, because remember, neutral axis is that line which does not undergo any change of length, right? So that length of that line stays as dx. But if you take a line which is above the neutral axis, essentially in the region where you're having compression, that line contracts. That we had seen that the top part of the beam, the upper half of the neutral axis undergoes compression, the bottom part, the bottom half is undergoes tension, that is there, right? So now let's start to write some of the formulations that we may get that when we are looking at these kinds of beams which are undergoing this level of bending. So now, as we discussed, so if we mark some of these points which are there, this EF, I'm looking at this line segment EF over here. So the original length of EF that you see here is just dx, because it has undergone not gone any deflection. So the original length of EF is dx that we have, and which is, again, if you have to write dx, which was originally it was dx, is the same as the length of this neutral axis, and the length of this line segment along the neutral axis has stayed as dx. But now in terms of this d theta and in terms of this radius of curvature, remember rho is the radius of curvature, I can write dx as nothing but equals to rho times d theta. Correct. Now let's take a look at the same line EF again. Now this line EF, what is the deformed length of EF? Now this EF is at a distance y from the neutral axis. So this is at this distance y, and after it has bent, after this beam has bent, this EF has undergone a shortening. That's what we have seen, that above the neutral axis the lines undergo shortening. So, and what is going to be the length of this EF over here? That can also be easily calculated. That is going to be rho minus of y times d theta. So EF is going to be rho minus of y d theta. Now if we have to calculate the longitudinal strain for the line EF, how do we find that? What do we mean by strain? Strain is the change in length divided by the original length. So if we have to write that, that becomes equals to, so the change in length will be rho minus y d theta minus rho d theta, so it will be minus of y d theta, and the original length is your dx that we have over here. So it is going to be minus of y d theta divided by the original length dx, that is rho d theta, times rho d theta over here. So that becomes equals to minus y divided by rho, and we know that 1 divided by rho, or 1 divided by the radius of curvature, is simply the curvature kappa. So that is equals to minus of kappa times y. So my epsilon x becomes equals to minus of kappa times y. So this is an important formulation that is there. Sigma we know that my sigma is related to E times epsilon. So this is from Hooke's law, which we know already, right? So how does sigma x vary? So sigma x, now you see that how beautiful this concept is. We are looking at the bending, but we are looking at normal stresses and strains, right? So there our sigma x becomes equals to minus of E epsilon x, which is equals to minus of E kappa y. So what does that tell you? That tells you that from both, if you take a look at this expression or this expression over here, right, it is a linear function of y. So what does that mean? That means that as you are moving away from the neutral axis, your strains increases and correspondingly your stresses also increase in a linear manner, right? It's a function of the kappa y. Now remember, this is valid only within that limit of proportionality that you have. If you're going into the non-linear region of the stress strain curve, this does not hold true anymore. This is only valid within the proportionality limit of the Hooke's law. So let's maybe make a quick note of that one, that stresses and strains, so sigma and epsilon varies linearly with distance from the neutral axis. Neutral axis is NA. So here also, let's just mark it. This is my neutral axis, NA over here, and this is NA. Right. Now the important thing to note over here, that when y equals to 0, that is y, remember, is the distance from the neutral axis. When y equals to 0, then your strain is 0, stress is 0. So at the neutral axis, no stress, no strain, and that is the reason why the neutral axis does not go any contraction or elongation. It just stays what it is. Above the neutral axis, you are having a compression. And also very important to note one thing is the reason why we are getting this negative sign. This reason why we are getting this negative sign is that we have considered a point which is on the above, which is undergoing compression. So that's why if you look at that original where we are getting this negative sign, it comes over here. So the change in length is actually a compressive change in length, and as per convention we mark compressions as negative. Now suppose if you were taking this line below, this would come out as positive. So don't be too bogged down by the signs, as the sign means that sigma x is compressive. Here negative means sigma x is compressive, and epsilon means that it is undergoing shortening in length. If it's a positive, that means that it is undergoing tension and the section is undergoing an elongation. So that's the only reasoning behind this particular sign, and no other reasons. If you understand the logic, you get a hang of it pretty soon. right? So now this is the general formulation so that we get. So if you have to just summarize quickly what we got is that, and this is a great way to visually see. So you see this entire section, what was plane over here, this section was, you know, this rectangle. After bending, the plane section has remained plane and it has just bent something like this over here. Now as a consequence of that, at the middle line you do not have any stress or strain, right? So about this neutral axis, so you have essentially this plane, this is the neutral axis which is, you know, undergoing. So you have a plane along the length of the beam which does not undergo any change of length, no compression, no tension, but as a consequence of this section moving like this, you can see that the top part is, it's very simple to visualize as well. So if you do something like this, you see the top part is undergoing a compression, bottom part is undergoing a tension. And how does it happen? Is that this is the general formula for that. This is, you know, you are having this compression over here, so you have this epsilon x is change in length, and this is the part where you are having the tension. And another way to say, so you might be wondering in your mind that in the bottom part, will I get a positive or a negative? Of course you will get a positive, because you see, if this is your zero line over here, you're measuring from here, so your positive y you have measured vertically up. So if you are taking any point below that, you have substituted negative number over here, it will be minus y, and you put that minus y over here, so minus of minus y becomes positive. So it is, so don't be bogged by the sign. So sign is just to indicate this is a compressive or a tensile. This is the general formula. If you're looking at, you know, places which are above the neutral axis, you have a negative stress indicating compression. Below the neutral axis, your y is negative, and if you put it back over here, you will get your sigma as positive, that is indicative of tension over here. Now if you want to look in 2D, the same figure, for example this one, if you are looking at from this particular angle in 2 dimensions, this is a good way to visualize this. And most of the textbooks now you're seeing, and later when you will study concrete design, you will see they represent it like this. So the top part, so this is again my neutral axis which I'm looking at. So let's just quickly mark that. So this is my neutral axis, right? So above the neutral axis you are having a compression, and below the neutral axis you are having a tension that is there. So these are the two of the important relationships that we saw, right? Now next we are going to use these relationships again, especially the one for the stress, to derive what is known as the flexure formula. So let's go ahead and take a look at how to derive the flexure formula. Now what we are going to look at is the fundamental flexure formula, also known as the bending formula, which gives you a direct correlation between the normal stress and the applied bending moment. Now we have already seen that at every section of this beam that is bending, the normal strain, it varies, and the normal stress varies linearly from the neutral axis as you go above or down, right? We have not seen that how these strains or the stresses are related to the bending moment. The flexure formula essentially gives us that, right? And to derive the flexure formula, we are essentially going to make use of the first two equations of statics. The first equation of statics essentially is the force equilibrium, and the second equation of statics is the moment equilibrium. Now before we go ahead and write the equations and solve and derive them, and what you will see comes out of the first equation of statics is essentially the location of the neutral axis. Now can you imagine that when this beam bends, right, so we have the top part, the length which is contracting, the bottom part which is expanding, and in between you have this neutral axis somewhere between the top and the bottom, which, you know, the length remains the same. Now can you and length remains the same, and also the stresses and the strains are zero. So can you intuitively think that along which line or along which point does the neutral axis lie? Yes, you probably can guess it from intuition that it lies about the centroidal axis. Now the first equation of statics, or the force equilibrium, gets that, and the moment equilibrium essentially helps us get closer to the flexure formula that is there. Okay, so let's start with the first equation of statics that is there, and then we'll look at the second equation of statics. Now the first equation of statics, as I said, is the force equilibrium, and we are not going to write and derive all the single equations, because these are, you know, essentially precursors to getting to the flexure formula. So we'll quickly skim through those. So as you can tell, the force equilibrium is essentially that if we take this cross section, see our beam is bending, and as long as it's prismatic, it does not have to be rectangular. We are looking at a prismatic section. The section itself is in equilibrium, and say at a a distance y, my stress is sigma x that you have over here. So the force that is acting, force is stress times area, that is sigma x times dA. Now if we integrate that over this entire cross-sectional area that is there, that must be equals to 0, because the section itself is in equilibrium. It's just bending, section itself is in equilibrium, it is not translating anywhere. So if we have to expand this formula that is over here, remember this sigma x, which we have already seen from the strain from that last lecture, that sigma x is nothing but the modulus of elasticity times your curvature times y times dA equals to 0 over here. So this expression essentially leads to this particular relationship, that is y dA must be equals to 0. So what does this essentially mean? This means, and this is over again the entire area that you're looking at, right? This essentially means that the first moment of the area with respect to the z-axis. So you are calculating this about the z-axis over here. So that is equals to 0. So that means that z-axis, the point about which you are making the forces 0, must pass through the centroidal axis. So that means that since the z-axis is the neutral axis, so the neutral axis must pass through the centroidal axis, which exactly matches our intuition that the neutral axis must pass to the centroidal axis, and along the neutral axis we do not have any change of length, we do not have any strain as well as the stress. So this is one of the first from the first equation of statics we get this important observation. Now let's take a look at the second equation of statics that is there. Second equation of statics, as we mentioned, is this is the moment equilibrium that we have. Now similar to the force, now if you take the moment, we are looking at the same section that you have over here. Now previously we did that your summation of sigma x y summation of sigma x dA was equals to 0. That was the force equilibrium. Now we are calculating the moment. Now remember, this moment overall must match this bending moment that is over there. So that is given. So as a result of these forces, now from this force distribution, can you sort of tell, because from these compressive forces you can have an equivalent compressive force, from this tensile you can have an equivalent tensile force, and they will be separated by a distance, and that will give rise to this moment that is there. But leaving that aside, if you go ahead with the basic fundamentals, what you have, your sigma x times dA times this distance y, that is the moment of the force which is acting on this small area over here. As similar to before, if you integrate over this entire area, and if you substitute this sigma x that you have over here, right, because sigma x we know is minus of epsilon minus of this curvature, which is kappa, times the epsilon times y. So y becomes a y square. So eventually if you simplify this eventually leads to this particular relationship over here, and this is important. This will lead us to the flexure formula that we have over here. Now from this relationship, what you can tell, that this relationship also sort of leads you to the relationship that your curvature, that is kappa, right, is 1 over your radius of curvature is equal to m divided by ei, right? Now what is this I as derived in this relationship? Because if you see this relationship over here, eventually it simplifies to integral of y square d, and this integral of y square d is nothing but I. So this is nothing but your area moment of inertia, if you remember from what you have studied in +2, and I will give you some other references as well. This is the area moment of inertia, and this you are calculating about the z-axis in this particular case, right? So it is IZZ if you want to say. So this is about the z-axis over here. So you get this relationship that you have over here. Now this relationship is essentially going to lead you to the flexure formula. So let's go ahead and see that how the flexure formula is derived. So let's keep this relationship in mind. Let's go ahead and maybe write this equation as well in the next page. And this is the relationship again rewritten over here. This is what we just wrote in the previous page over here, that remember, this is again our positive convention for the moment, this is the negative convention for the moment and the curvature, positive convention for the moment and the curvature, and it also tallies if you see, right? Because when you have this positive moment, you are seeing the positive curvature which happens, and you see kappa comes out as positive. When you have a negative moment over here, your kappa will come out as negative. Over here the negative curve. So if you put m as plus, kappa comes out as plus. If you put m as minus, kappa will also come out as minus over here. Now let's take this relationship ahead and write the Flexure formula. Remember, when we started this lecture, we said the Flexure formula gives you a direct one-to-one relationship between the stress and the moment, right? So let's go ahead and write maybe this relationship which we just saw, that our kappa was equals to m divided by ei. This is what we just derived in the last page, right? Also remember, from our expression between the stress and the kappa, what was that relationship? That was sigma x was equals to minus of kappa epsilon y. Because remember, the strain was your y times kappa. So your stress from Hooke's law was E times y times kappa, which is slightly rearranged. So kappa times E times y. Now, if you take these two relationships that are there, this one and this one over here, and if I take this guy kappa and I put it in this one over here, now using these relationships, the left and the right, I can write the famous Flexure formula as sigma x. Let me just rewrite that again, that sigma x is equals to minus of m y by I. So this is your Flexure formula. So now you see that from this formula you have a direct one-to-one relationship between the stress and the applied moment, and it's pretty intuitive if you think about it. For example, we said that at the neutral axis level, that is at y equals to 0, you have no stress and the no strain, whereas if you are moving away from the neutral axis, if you are losing at the y top or the y bottom, you will have the maximum and the minimum stresses. Now depending upon the moment, of course, it will be either the maximum tensile or the maximum compressive, but you get the overall idea. Now before we move on, one more thing which I would like to note is this term ei, which we will see is mentioned in many of the textbooks. Can you guess what is this ei called? Now remember, when we studied axial load, the denominator ae was axial rigidity. When we studied torsion, we had a jg, which was the torsional rigidity. Now ei, see, the higher the value of ei over here, it is, the higher, the lesser will be the value of kappa. So to get the same amount of kappa, you have to apply more and more amount of moment for a section which is a higher value of ei, right? So this product of the Young's modulus E and I, right, which is the area moment of inertia, is known as the flexural rigidity. This is an important thing to know. It's an important terminology. In many books, they just give you the flexural rigidity and you are supposed to know what that is, flexural rigidity. So now that we have the Flexure formula, at our disposal, let's go ahead and take a look at, a couple of examples of how it works out to be. Essentially something like this. So we have, see, this is a beam. It can be rectangular, can be circular, prismatic. That's all. The only thing that matters over here, see, the shape of the section, whether it's rectangular, circular, trapezoid, or anything, comes into play when you compute the I, the moment of the area moment of inertia, right? And the numerator just depends on this distance. So here you see the maximum stresses, sigma 1 and sigma 2, happens at the top and as at the bottom over here. So C1, there you have the maximum compressive stress. Now this is also an interesting page because here it shows that, this form, you see this negative sign over here. So if you put C1, since we said that y going from here to the top is positive, so if your moment is a positive bending moment, this is positive over here, C1 will be positive, so your sigma 1 comes out as a negative, so that means you have a compressive stress, right? As opposed to when you are going below over here, M is positive, but here C2 is negative over here, so overall it becomes a positive, so that means your sigma 2 that you get over here is a tensile stress. Now look at correspondingly opposite kind of a moment, if you have a negative moment, the same thing holds, because in the negative moment, say you are going up, so you expect the sigma 1 to be positive, right? But your m itself is negative, so you put a negative m over here, so that becomes negative, negative becomes positive, and your c1 is just c1 and you're going up is a positive c1, so your sigma 1 will come out as positive in that particular case, right? And that is a tensile stress, and similarly your sigma 2 will come out as negative. Now one important thing to note here is that often in when engineers do the design, usually they're given a designer's handbook, and I will show you a couple of pages of that one. The designer's handbook essentially has these values over here, because see, at the end of the day you're looking at a section. So the characteristics of the section which you should consider, or which should come across your mind to calculate the maximum normal stresses at the top or at the bottom, is how the section is, the shape of the section, rectangular, circular, trapezoid, or anything else, right? So that dictates your I. And also the maximum stress depends upon the distance, right? Like the top and the bottom. So usually these two quantities that you see over here, this guy, right? These two guys, they are usually, clubbed together in one single unit in designer's handbook, and that is known as the section modulus S, which is, these two guys over here. The section modulus essentially tells you, see, your I, regardless of whether you're looking at the top or at the bottom, I is same. I just depends on the section. So I divided by C1, that is I divided by this top distance, and I divided by C2, they are known as the section moduli. So you have two section modulus for every section. So it is just the ratio of the moment of inertia, the area moment of inertia, to the distances from the neutral axis to the top and from the neutral axis to the bottom. So these are the two section modulus that are there, right? But at the end of the day, in a nutshell, so overall in a nutshell, your sigma, if you just write in for the magnitude, if you're just considering the magnitude, your sigma is nothing but the mod of sigma is nothing but the modulus of my by I, where y is the distance from the neutral axis, and so this sigma is positive when it is tensile, right, and it is negative when it is compressive. If you are too bogged down with the signs and what is positive and what is negative, no need to worry about it. You just calculate the modulus, you just take the respective distances, and from your intuition, from how the beam behaves, you tell whether the top is in compression or the bottom is in compression, or the top is in tension or the bottom is in tension. As simple as that, right? And accordingly, if it's a compressive, you just put a negative sign. If it's tensile, you just put a positive sign. Very simple, right? Okay, all right, so let's just go ahead and look at some of the very common kind of sections. What are the most common types of sections in beams? Rectangular section, circular section. Let's just write a couple of tidbit formulas for those. For example, if you have something like this over here, for the rectangular beam, you know that your I is essentially, in this particular case, is 1 by 12 BH cube. The unit of I is is distance raised to 4, so mm raised to 4 or meter raised to 4 and so on. And your section modulus is what? Here S1 and S2 is the same, because it's a rectangular section. Your neutral axis is equidistant from the top and the bottom, so your S1 equals to S2 equals to what? It is the ratio of I times that that C, that the distance of the maximum of the topmost or the bottommost fiber from the neutral axis. So it will be in this case H over 2. So that is nothing but B H square by 6 once you put that I equals to 1 by 12 base. So this is for the rectangular section over here. For the circular section, you have a similar kind of a formula that is there. So for the circular section, your I is equal to pi d raised to 4 divided by 64, right? And your distance from the neutral axis, the top fiber and the bottom fiber, is nothing but the diameter divided by 2, or the radius. So you get your S1 is equals to S2 equals to I divided by d over 2, which essentially leads to pi d cube by 32, right? So this is for the left one is for the rectangular section, the right one is for the circular section. Now is particularly no need to remember the section modulus at this particular time, at this particular point. Later when you do design, it will be more helpful, but just remember that fundamental formula, and I will write it again just to bore you. So our overall the most important fundamental formula is sigma x equals to my by I. This is the modulus I'm looking at, right? If it is positive, if you're looking at the the compressive stresses, it will be a negative sign. If you're looking at the tensile stress, it will be a positive sign. Simple. Now talking about the different the area moment of inertia different sections can have, these are the general formulas for that one, which you're quite familiar with. If you are not, I recommend you flip through some of the very basic standard textbooks in your +2 or any of the engineering or any of the mechanics of materials books. If you flip through the last pages in the appendix, you're usually given these bunch of formulas. So this is your IZ. So if you have a section on the Z axis, this is your IZ, what we just said, that IZZ, remember that it is integral of I square dA, IY integral of Z square dA. And also you will remember the parallel axis theorem, that if you have your I about the centroidal axis and if you have to calculate it about another axis, that is the I about the original axis but area times that distance square. So you know these things. If you are unfamiliar, just go ahead and brush it up or look into the appendix. They give proper explanation in any mechanics of material textbook, and you will see that it gives a proper, for example, the book by Gear and Goodnow, Mechanics of Materials, it gives a very nice treatise of the review of the moment of inertia that is there. Now, as I said, within these books you will also see these kinds of tables which gives you for the different sections. Now you should be familiar with how to compute. If you get a odd section which is not rectangular, not triangular, not circular, not trapezoid, you should be in a position to calculate the moment of inertia for that particular section. So make sure you're familiar with that, right? So in the standard textbooks you have all these different formulas. And the last thing which I'm going to say in this lecture, that remember that we talked about the section modulus for the different design sections. What you have over here are two very typical steel sections. Next time you go around, you take a look at steel structures, you will see there are several of these H sections or I sections and these channel sections which are there. And these pages that you see these are for the European standard channel, because this is a standard channel section, this is a standard beam section that you have. And for this, remember what I said, what you're mostly interested about is the section modulus S, and that depends upon the moment of inertia and the distance from the top and the bottom fiber. And if you see any of these tables, and this is just to give you an example, we're not going to particularly deal with some of this of these design table, but just to give you an example of how this looks like. So for any particular channel section, see, it gives you what are the different dimensions of the section, and also it gives you these guys. This is this S1 over here, S2 is sort of overlaid by this one, but you can see over here, see this S1 and S2, right? So overall, I hope that you are now familiar with the flexure formula, which gives you a direct one-to-one correlation between the stress and the moment. And if you know the stress, you can backtrack and calculate the strain as well. So it is equals to, the stress is equals to my divided by EI, where the denominator EI is the flexural rigidity. Now we are going to take the flexure formula and we are going to do a couple of example problems to clarify the concepts.